Jk flip-flop using SR flip-flop and AND gates. This Jk flip-flop can be constructed using clocked SR flip-flop and two AND gates. The inputs to the AND gates forms J and K, and one more input to these AND gates are from the output of the clocked SR flip-flop. Thus, the output of gate 1 becomes S, which is equal to J into Q bar. The output of gate 2 becomes R, which is equal to K into Q. The truth table of Jk flip-flop is when clock is 0, J and K don't care, it enters into hold state. Similarly, when clock is 1 and J and K are 0, it enters into hold state. When clock is applied, J is 0, K is 1 is a reset state. When clock is applied, J is 1, K is 0 is a set state. The last condition, when J is 1, K is 1 with the clock applied, the Jk flip-flop enters into toggle mode. Thereby it avoids the drawback of SR flip-flop, that is the invalid state. Let us see the working of Jk flip-flop. Case 1. When clock is not applied, irrespective of J and K inputs, the flip-flop enters into hold state, because when clock is not applied, the flip-flop will be inactive and the output of the flip-flop will be in hold state. Because when clock is 0, irrespective of S and R, the clocked SR flip-flop is a hold state. Thus, when clock is 0, J and K don't care conditions, the flip-flop enters into hold state. This can be referred with this clocked SR flip-flop diagram too. When clock is 0, irrespective of S and R, the flip-flop enters into hold state. Case 2. When clock is applied but J and K are 0. Because one of the input to the AND gates are 0, S will be 0, R will be 0. Because clock is 1, S is equal to 0, R is equal to 0 is a hold state. For a clocked SR flip-flop, the output of the Jk flip-flop will be in hold state with this condition. Next, when clock is applied, J is 0 but K is 1. In this condition, let us take the previous state as a reset state and a set state. Then we will come to a conclusion what is the final state of Jk flip-flop under this condition. In the first condition, let us assume a flip-flop is previously reset state. That means Q is equal to 0, Q bar is equal to 1. Now, from the diagram it is clear S is equal to J into Q bar. If we apply those values, J is 0, Q bar is 1, that means S is equal to 0. Similarly, R is equal to K into Q, that means 1 into 0, that means 0. Again, we got the state as a hold state. That means Q will be 0, Q bar will be 1 even after the application of the clock pulse. Whereas in the second case, we assume the flip-flop was in set state previously. When Q is 1, Q bar is 0, S becomes 0, R becomes 1. That means when S is 0, R is 1 for a clock, SR flip-flop, it is a reset condition. Thus, ultimately, if we observe both the conditions, condition A, that is when reset condition was previous, Q is equal to 0. Condition B, when set state was previous, now also Q is equal to 0. Hence, finally, the output is in Q is equal to 0 state, hence it is called as reset state. Next, when clock is applied, J is equal to 1, K is equal to 0. This is a set state. Again, let us consider two instances. One is a set state previously and another is a reset state. When set state is there in the previous set state previously, that means S is equal to J into Q bar will become 0. R is equal to K into Q, that is 0 and 1 becomes 0. In this case, clock is applied, S and R are 0. So it is a hold state. Hence, the output of the flip-flop will be Q is equal to 1 and Q bar is equal to 0. Whereas in the previous state as a reset state condition, that is when Q is equal to 0 and Q bar is equal to 1. Assume the previous state is a reset condition, that is Q is equal to 0, Q bar is equal to 1. Then S becomes 1 and R becomes 0. For a clock SR flip-flop, if S is equal to 1, R is equal to 0 with the clock pulse, it is a reset set condition, that is Q is equal to 1, Q bar is equal to 0. That is, if we observe in both the cases, when the flip-flop was set initially, it was a set state finally. When the flip-flop was reset initially, then also it is a set state. So, finally, when clock is 1, J is 1, K is 0, it is a set state. The last condition, when clock is 1, J is equal to K is equal to 1. This avoids the invalid state of the JK clocked SR flip-flop. Again, here we can take two conditions. Case 1, when the flip-flop is in a set state previously, that is Q is equal to 1, Q bar is equal to 0. S becomes 0, R becomes 1, which is a reset condition. So Q is equal to 0, Q bar is equal to 1. Earlier it was a set state, it has become a reset state. Whereas in the second condition, when previous state is a reset state, that is Q is equal to 0, Q bar is equal to 1, S becomes 1 and R becomes 0 with the data given to the equation. Hence it is a set state. So Q becomes 1 and Q bar is equal to 0. If we observe in these two conditions, when Q was 1, after the application of the clock pulse, Q becomes 0. When Q is 0, after the application of the clock pulse, Q becomes 1. That means the output of the flip-flop toggles between set and reset state. Continuously, if you apply the clock pulse, the flip-flop will oscillate between set and reset state. Hence, this state is called as toggle state. This is the importance of JK flip-flop. Coming to the timing diagram and the block diagram. This block diagram is shown here for a PGT, that is positive going transition. With the clock pulse applied, this arrow mark shows that it is a PGT pulse. K and J inputs, the output. With the application of the clock, K is 0, J is 0. That means flip-flop should be in the previous state. We have assumed initially Q is equal to 0. So from here to here, that is from one PGT to the second PGT, it will be in a hold state because J is equal to 0 and K is equal to 0. At the second PGT, K is 0, J is 1. That means it is a set state. For the third PGT, K is 1, J is 0. That means it is a reset state. Fourth PGT, K is 0, J is 0 is a hold state. So it holds the reset state. The last condition, with application of PGT, K is 1, J is 1. It is a toggling state. Hence, from reset, it will toggle to a set state. This is the timing diagram of clocked JK flip-flop. The drawback of Jk flip-flop is a race around condition. Race around condition is nothing but the uncertainty of the output at the end of the clock pulse is known as race around condition. That means the flip-flop response is fast than the clock pulse. Suppose if we use a level triggered Jk flip-flop, the output toggles n number of times before the clock pulse becomes inactive. By this, how many times it has toggled we cannot predict. That means it is uncertain to predict whether the output will be in set state or reset state. This uncertainty of the output at the end of the clock pulse when clock is 1, J is 1, K is 1 is known as race around condition. This is the main drawback of Jk flip-flop, which can be avoided or overcome by two ways. One, using edge triggered flip-flop. The second one is master flip-flop. Next video I'll be explaining about master slave flip-flop. Share, like and subscribe. Thank you for watching